Welcome. In this video we're going to talk about factorial design and ANOVA. So this is an extension of the one-way ANOVA, which you'll recall has one independent variable. More specifically, the one-way between subjects ANOVA has one independent variable and an interval ratio dependent variable, and we want to compare the mean levels of that dependent variable across the levels of that one independent variable. So that this is an extension for when we have more than one independent variable. We'll keep it in this lecture to situations where it's a between subjects design, meaning that participants are in one condition but not the other, or not any of the others in the design. In future lectures we'll get into situations where participants may be in multiple conditions, and those will be called either within subjects or repeated measures design. And by analysis of variance, basically what we're doing is we're trying to analyze the variance in the design to see if there is more of an effect of something, which would basically boil down to differences between the group means, than there is error, which would basically boil down to differences within the group means. But there's various ways that we divvy up the variance in a factorial ANOVA that gets a little bit more complicated than in a one-way ANOVA. So starting with a simple factorial ANOVA, if there is such a thing, here we might have an example of what we will call a 2 by 2 design. So let's just say we wanted to see how physical attractiveness and income affect likability, some measure of likability. And so we have two levels of each of these variables. We have people who, let's say, stimuli that participants are asked to look at, who are either predetermined to be high or low in terms of physical attractiveness, and we also present information about their income, which indicates that their income is either high or low, and we want to see how that affects, let's say, a dependent variable such as likability. Now this would be called actually a 2 by 2 design. Why a 2 by 2 factorial design? Because there are two levels of one independent variable and two levels of the other independent variable, and here hypothetically our dependent variable is likability. So if this were a between subjects design, which is what we're going to be dealing with in this lecture, a participant would, let's say, show up for the experiment and would be randomly allocated to encounter only one of the conditions in the cell. So let's say you showed up to participate in the experiment, you were randomly assigned to the low income, high physical attractiveness stimulus. So in a between subjects design, participants will only encounter one cell of the possible cross tabulation of the independent variables. So in life and in research, there's usually more than one variable or factor that affects an outcome. So that's why it becomes important to look at more than one independent variable at a time, and also to look at how those independent variables might interact to predict or to cause a outcome or dependent variable. So what are some advantages of having multiple independent variables? Well, one is I mean, it's arguable whether or not this is an advantage, but one is that you can study multiple main effects at once. So there's kind of an economy of design in that you can look at multiple main effects, multiple factors in one experiment. So you would need fewer participants than if you were to run separate independent studies. Probably more importantly, we can examine interactions among the independent variables. So by interactions, what we basically mean is, does the effect of one independent variable on an outcome depend upon or is contingent upon the level of another independent variable? So going back to our previous example, does the effect of physical attractiveness on likability depend on income? So let's say like people who have low income, maybe the effect of physical attractiveness is stronger than for people who have high income. Maybe physical attractiveness is less of a factor. It might still be a factor, but it would be a weaker factor, right? So hypothetically, that would be an interaction where the effect of attractiveness on likability depends on the level of income one has. So interactions can usually be closer approximations to real life. Probably in real life, in this lecture, we're just going to talk about two-way interactions, so interactions between two independent variables. But in real life, maybe there are, routinely four-way or five-way interactions that get really kind of complicated to study from a methodological and a statistical standpoint. But basically, in these types of designs, you're testing hypotheses involving main effects and also interactions. When an interaction is present, the interaction hypothesis is typically the one that is focused on, because the main effects in an interaction are contingent, really, or depend upon the nature of the interaction. So when an interaction is present, it's important to focus on the interaction effect, but usually researchers will also interpret the main effects. Alright, so let's move forward with a slightly more complicated hypothetical example. Let's say researchers examine the differences between art therapy, behavioral modification therapy on classroom disruptive behavior, and found that both decreased the behavior when compared to a no treatment control group. So our independent variable will be treatment type. So we have a control group, we have a behavior mod, and we have art therapy. The outcome is the dependent variable is classroom disruptive behavior. Let's say that, however, neither therapy was different from the other, and the researchers aren't satisfied with their findings and wonder if there's another variable or factor that should have been taken into account. So they want to create a factorial design with their treatment variable, or the treatment or condition independent variable. So they decide that it might be gender, like it might depend on gender whether or not art therapy or behavior mod would be more effective. So they want to add gender to the design. And they expect that men would respond better to art therapy and women would respond better to behavior modification for whatever reason. This is just a hypothetical example. And that there would be no differences in response to the no treatment control condition, which seems logical. Alright, so let's ask these questions once more. What is the outcome of the dependent variable in the previous example? That would be classroom disruptive behavior. And what is the independent variable or variables, and how are they defined? So there are two. One, as we said, is treatment group, which would be no treatment, art therapy, and behavior modification. And the other independent variable, which is not really an experimental independent variable, it's more like a naturalistic group, would be gender, which is male and female in this design. So looking at this in one of these sort of window box designs, as they're often called, we see that here we have the treatment group, which is no treatment, art therapy, behavior mod, and here we have our gender, male and female. And this would be considered a 3x2 factorial design. So we could be looking at some different things as we analyze the data. One would be the main effect of treatment. Another would be the main effect of gender. So those would be two potential main effects. So that would be just differences. The main effect of treatment would be looking at the differences between the means of classroom disruptive behavior across treatment types, basically ignoring or collapsing across gender. The differences for gender would be looking at the means for classroom disruptive behavior, basically are ignoring or collapsing across treatment type. Probably not terribly interesting, but nonetheless it would be included in the design. And then if you're doing this sort of analysis, Factorial, ANOVA, you're probably interested in the interaction. And the interaction would tell us does the effect of one IV, let's say treatment type, on the dependent variable, which here is classroom disruptive behavior, does it depend upon the level of the other IV? So here, is it dependent on gender? So in designs where there is a significant interaction, it's important to interpret um, the interaction. The main effects are contingent. If there is an interaction, the main effects are contingent or dependent upon the interaction. So the interaction is probably going to be the focal point of the interpretation of your results, but nonetheless, you still will report the main effects. So as we've already noted, we use the number of factors and the number of levels per factor to describe the design. So the design we just looked at is a 3x2, so 3 conditions for therapy and 2 levels for gender. It's a 3x2 factorial design. So as you can see in this hypothetical design, there are 6 cells in the design. So there's 6 basically possible combinations of these 2 variables. We have control group male, art therapy male, behavior mod male, and we have control group female, art therapy female, and behavior modification female. Right. So in a 3x2 design, there are 6 possible conditions. In here we see inside of the cells are like hypothetical values for the dependent variable, classroom disruptive behavior. We would call those the cell means. So the cell means are inside of the design, whereas the marginal means would be the main effects. So to look at differences between the marginal means, so the means in the margins. So here we have means for control group, art therapy, and behavior mod. The differences between those, if there are, so collapsing across gender, that would be the main effect for the therapy group or the treatment group. We'll also be looking at a little later in the lecture things called simple effects. So for now, let's just say that simple effects are the effect of one independent variable at a fixed level of another independent variable. So main effects are the effect of the independent variable collapsing across the other independent variable. So let's assume there's only 2 independent variables. Whereas the simple effect is the effect of one independent variable at a fixed level. So what you see right now, boxed in red, is a simple effect of therapy group when gender is male, and here we see the simple effect of therapy group when gender is female. And here we see now the marginal means for gender. So we see that the mean classroom disruptive behavior, ignoring therapy group for males, is 11.42, and ignoring therapy group for females is 11.5. Also, the grand mean tells us the overall mean, like ignoring all conditions altogether, just like what is the mean for classroom disruptive behavior. We can also look at the simple effect of gender, so the differences between gender when the therapy group is the control group, so that would be the simple effect of gender for the control group. This would be the simple effect. The differences between those 2 marginal means would be the simple effect of gender for the art therapy group. And here we have the simple effect of gender for the behavior modification group. So we could be looking at main effects, and if we're looking at interactions, chances are we're looking at differences between these simple effects. And again, the simple effects are the effects of one independent variable at a fixed level of another independent variable. So just kind of looking at the means without doing the ANOVA, does it seem like males and females respond differently to the therapy interventions, or depending upon which group they're in? So basically, we'll be looking at the simple effects of gender at each therapy condition. That's basically what this question is asking us to do. So is there a noticeable difference between males and females for the control group? Not really. They're roughly around 17. Their score for classroom disruptive behavior. For the art therapy group, we noticed that females have much higher scores than males. And for the behavior modification group, we notice there's a difference, but the difference has reversed. So there does seem to be, if you will, a difference between the differences. So basically a difference between the simple effects, which is indicative of a statistical interaction between these two independent variables. So in this table, we have the cell means, we have the marginal means, which allow us to assess the main effect, the marginal means for therapy, and we have the marginal means for gender as well, and then of course we have the ground mean, which is the mean, which is ignoring all the conditions to get all together. When there is an interaction present, which is kind of the purpose of doing the factorial ANOVA, which we haven't gotten into the formulas for that or the interpretation of it yet, just kind of the conceptual background for it. When there is an interaction present, though, it is helpful to inspect either bar graphs or line graphs to get an idea of what the nature of the interaction is. So here we can kind of see in these hypothetical data, there's no difference between males and females in the control group. In the art therapy group, it seems that the females are scoring higher than the males, whereas in the behavior modification group, that difference has flipped around on us. So we could also look at this as a line graph. Probably since both IVs are categorical, it's preferable to do a bar graph. By default, or as one of the options in SPSS, it will give you these sorts of bar graphs, so you can look at them and see that, okay, in the control group, there seems to be no difference between males and females. In the art therapy group, there is a difference, such that females score higher, and then there is a crossover between the lines here, where the males score higher in the behavior modification group than the females. We could, so just to simplify things, we're going to cut off the control group and focus on the comparison between males and females at the different levels of art therapy. We can see that here at art therapy, the females score higher than the males, and behavior mod, the males score higher than the females. So this is kind of flipping it around. We can also take kind of the average between the two lines for collapsing across two conditions and visualize the main effect. It's not the easiest thing to visualize in a line graph, but it is possible. So this is flipping it around, and we see that the differences between the art therapy groups are basically as we described them before. Alright, so what we've been looking at is what's considered a crossover interaction, and that's when the two, when the effect of one independent variable on the dependent variable is actually reversed by the level of another independent variable. So that would be like a specific type of interaction called a crossover interaction. So in this example, there would be no main effects, but an interaction. So now we're going to look at some other hypothetical possible outcomes. So here we have a main effect of therapy, because you can see on average the behavior modification means are higher than the art therapy means, but that's basically driven by the male condition, or the male group. So here we have an example of a main effect of therapy, no main effect for gender, and an interaction because the males are responding differently to the therapy, whereas the females are responding the same to the therapy. Here we have an example where there's no main effect of therapy. Basically, the therapy effects are equal across art therapy and behavior mod, but if you look at the interaction, there is an interaction because for the behavior mod group, For the females, behavior mod is resulting in lower scores, and for the males, behavior mod is resulting in higher scores. And here we have a main effect of therapy and a main effect for gender and an interaction effect. So we see that there's a difference between the art therapy and the behavior mod group, and there's also an interaction. Is that the same as the previous slide? Well, the previous slide had no main effect for therapy because they equaled out. Where this one, it doesn't quite equal out because the average for the behavior modification group would actually be higher. Alright, here we have no interaction. No interaction is basically when the lines are more or less parallel. So we have no interaction, but we do have main effects for gender and main effect for therapy. We can see the main effect for gender because the lines are separated from each other, where the males are scoring on average higher than the females. And we can see the main effect for therapy group because the behavior mod groups are a bit higher than the art therapy group. But there's no interaction because the effect of art therapy on classroom disruptive behavior is more or less similar across both genders. So here we have an example of the main effect for gender, but no main effect for therapy and no interaction because the lines are more or less parallel. And here we have probably the most boring result where there's basically a main effect for therapy, or actually no, this wouldn't be the most boring, but there's a main effect for therapy. You see that the behavior mod group scores higher than the art therapy group, but there's no difference for gender, and the lines are on top of each other there, so they're basically parallel. And then here we have no main effect of therapy, no main effect of gender, and no interaction effect. So this would be a situation where basically all the means are more or less identical or very similar and very close to the grand mean. So there's basically no effect of any of our independent variables on the dependent variable. A sad situation if you're the researcher for this sort of study. It does happen, but it's usually not what you're looking for if you're conducting research. Alright, so just take a step back. A factorial design contains the conditions formed by combining each level of one IV with each level of another IV. Actually, a factorial design can have more than two IVs, but for now we'll keep it at two IVs. A simple effect expresses the difference among the means for one IV at a fixed level of the other IV. So before, when we were looking at the effect of treatment condition at male versus at female, that would be a simple effect. A main effect expresses the differences among means for one IV averaged, collapsed across, or ignoring the other independent variable. So basically, how does this IV affect the DV? Almost like a one-way ANOVA, because you're ignoring the other independent variable, although it's a bit more mathematically complicated than a one-way ANOVA. And then finally, an interaction is present when the simple effects of one IV are different at different levels of the other IV. So an interaction is basically a difference in the simple effects. And just to reiterate one more time, a simple effect is the effect of one IV at a fixed level of another IV. Alright, so as most parametric statistical tests, or all statistical tests, will have assumptions. Some of the assumptions for a factorial ANOVA is that the IVs have more than two independent groups, and that for the type of ANOVA we're covering now, people are assigned to one level of each IV. So people are assigned to one cell or one group in the design. The outcome, or the dependent variable, must be interval ratio The distribution of the residuals, as we discussed with the one-way ANOVA, the distribution of the error terms should be normally distributed. And also, we also retain the homogeneity of variance assumption, which states that the variances of the groups that we're comparing, the cells in the design, are equal in the population and will be reasonably similar in our samples. So there is a test for this, which SPSS will perform if you ask for it, called Levine's test. That's one way to go about it. Another way is to just kind of inspect the variances and make sure that none are incredibly larger than the others. So if like one of the variances is like 4 times or more larger than the smallest variance, let's say the largest variance is 4 times or more larger than the smallest variance, then we've kind of got an issue with violating that assumption of the test. And as will be the case with pretty much every analysis we cover in this class, there is the assumption that the observations are independent, so that you're sampling independently. You're not sampling, let's say, from groups like families or couples or classrooms or something like that, where the observations might affect each other. For situations where observations are not independent, there are different approaches for analyzing those data that usually fall under what's called hierarchical linear modeling or multi-level modeling, which is beyond the scope of this lecture. Alright, so the assumptions for the Factorial ANOVA, we should take them seriously, but we have to also understand that in the wild, data are not always going to be perfect, and that some of these tests are fairly robust to some minor violations of the assumptions. So if you look at your distributions of the error terms, or not the error term, if you look at the distribution of the errors from your analysis, and you notice that it's not perfectly normal, it's probably still okay to interpret the results of the ANOVA. If your distributions for your variables are slightly skewed, it's no big deal. If the sample sizes are equal, we can actually relax the homogeneity of variance assumption a little bit more than if the sample sizes are very unequal. So for the most part, ANOVA is reasonably robust to slight violations of the assumptions, but in situations where the assumptions are grossly violated, one might consider instead using a non-parametric alternative test. So returning to our example, we are examining 3 different effects here: the main effect of therapy, the main effect of gender, and the interaction effect of therapy times gender. Within that interaction effect, though, there are multiple simple effects that we could investigate. So the interaction, if we have an interaction hypothesis, is basically going to specify that the gender will modify or affect the relationship between the therapy condition and classroom disruptive behavior. So the null hypotheses will be that for the main effect will be that there are no expected differences between the therapy group means. The null hypothesis for gender would be that there's no expected differences between the genders, and then the null hypothesis for the interaction would be that basically we don't expect the effect of therapy on classroom disruptive behavior to depend on gender, or alternatively we don't expect the effect of gender on classroom disruptive behavior to depend on therapy. So those are the null hypotheses. Usually if you're doing this sort of study, you're not hoping to support all of these null hypotheses. Instead, you're hoping that some form of alternative hypothesis will be supported. So non-directional alternative hypothesis for the therapy main effect would be that the therapy group means will have differences, that there will be a difference, at least one difference, I should say, among them. For gender, it would be that there would be a difference between the genders in terms of classroom disruptive behavior, and for the interaction it would be something like the effect of therapy on classroom disruptive behavior would depend upon gender. Now, if this was an actual study that you were doing, you would be more specific about how you expected therapy to affect classroom disruptive behavior differently depending upon the gender of the participant, and that's where you would actually specify a hypothesis for the different simple effects. So if we fail to reject, it basically means we haven't detected any differences between the means, if it's a main effect for that particular independent variable. If it's an interaction, we haven't detected a difference in the simple effects across the level of the other independent variable. If we reject the null hypothesis, it means that we have indeed detected something. Now there would be three null hypotheses that we would test in this design, so it would depend on which we would reject. If we rejected for the therapy main effect, it would mean that we found a difference between the therapy groups. If we rejected the null hypothesis for the gender main effect, it would mean we found a difference between males and females. If we rejected the null hypothesis for the interaction effect, it would mean likely that the effect of therapy on classroom disruptive behavior depends upon gender. So just like with the one-way ANOVA, we're divvying up the variability to look at differences between the conditions and to see what amount of variability is attributed to differences between the conditions and what amount of variability is more or less noise or error variance or within group variation. So basically the error variance is the amount of variability among the scores caused by chance or uncontrolled variables, and we detect this by looking at variability within groups, whereas for effect variance we look at variability between groups. We can see that there's variability between the groups for each IV, so the control group, the art group, and the behavior modification group. So that would be kind of the between group variance for a therapy condition. And then we have the between group variability for gender. And then this cell is not very visible, but then we see that within each cell we have variability within each cell, and that would be considered error variance, right? So kind of like the unreasonable expectation would be that if there were no error, then everyone would in a given cell would result with the same score. Of course, that doesn't happen, so we have variability within the cell, which results in error variance. So basically, what we'll wind up with is an F ratio to determine whether most of the variability or variance is due to effect or systematic or between group variance, and we'll compare that to see how much of that there is relative to the error variance or the within group variance. So the resultant statistic from an ANOVA is the F ratio, which basically divides the systematic variance by the error variance, or the between group variance by the within group variance. They basically mean the same thing. So if there's more systematic variance than error variance, then your F ratio will be greater than 1. That doesn't mean that it's statistically significant. It just means that there's more systematic variance than error variance. But if your F ratio is less than 1, then there's no chance that it's going to be statistically significant, because it means there's more error variance or within group variance than there is between group variance. So F must be equal to 1, greater than 1 to be significant. However, just because it's greater than 1 does not mean that it is. So the F ratio follows a distribution that we can look up the proportion of the area under the curve in the tail and determine what is the p-value for a specific F ratio depending upon the degrees of freedom of the test. So it gets a little complicated in the factorial ANOVA because there are several sources of variability. So it's not that we just have the one independent variable and then we have the within error, and we can very simply compute it. In a factorial design, we have variance that can be attributed to the between groups effect for therapy, the between groups effect for gender, and then also the between groups effect for the interaction. And then we also have the error variance, or the within group variability around the within group means, which all combines to, if we add them all up, like if we actually calculated all these by hand and added them all up, it would combine to create the SS total, or sum of squared total. So basically all these added together are partitioning up the total sum of squares, so the sum of the squared deviations from the grand mean. So here's the definitional formula. It's not completely uncommon to encounter this by hand in a stats class, but we're going to kind of avoid doing this by hand and do this in SPSS. So there's an additional tutorial on how to do the analysis in SPSS. And actually, if you were doing this by hand, you wouldn't use these definitional formulas. You would use some shortcut formulas, computational formulas, which make it a little less work. But let's just take a minute and look at some of these formulas to see if we can make sense of what these different ways that we partition the variance, what they actually mean. So the sum of squares total is basically the sum of the squared deviations of every individual score. So Yij just basically means every individual score in every group, minus the grand mean. So Y bar subscript T will be like the grand mean or the total mean, and then we would square the difference from every score from the grand mean and then add it up. So that's basically the total sum of squares. So the sum of the squared deviations of each IV's group mean. So this is each IV's group mean. So let's say Y bar subscript J might represent the mean for, it would represent separately the mean for control group, art therapy, and behavior modification therapy for that main effect. So we would look at how do the group means for each main effect separately. We'd calculate this for each main effect separately. How does that differ from the grand mean? So how much variability does the group mean have from the grand mean? We'd square that, multiply it by the sample size for each group, and then add up the total, and that would get us the sum of squares between, which would be like a raw measure of the effect for our be done for each main effect. Now for the sum of for the interaction does get a little bit more complicated because the group means collapsing across the other independent variable, looking at the deviation of the cell means from the grand mean squared and multiplied by the cell sample size. So it just gets a little bit more complicated there. But if we let's say if we had a data set and we sat a long time and looked at basically the difference group means from the grand mean squared, multiplied it by the sample size for each group, and then added it up for each group separately, did the same thing here, and then for the interaction, took the cell means, subtracted the grand mean separately for each cell, squared the difference, and multiplied by the sample size for the cell, and then added it up because we're doing it separately for it, the proportion of the sum of squares that is attributed to the interaction. And then we take those and create, well, actually before we take those and create the mean squared, we'll also need to calculate the sum of squares within. So basically the sum of squares within is our raw measure of error. So we would take the sum of the squared deviations of each score from its group or condition mean. So what's going on differently here is we have each and every score, but we're looking at its deviation from its group condition mean and then squaring that. So this is, instead of comparing to the grand mean, we're comparing it to the group mean or the condition mean. So to determine the statistical significance of an F ratio, we'll need a few more statistics. One is we'll need the degrees of freedom. The degrees of freedom total, which won't be of very much use, are the total sample size minus 1. The degrees of freedom within, or degrees of freedom error, is basically the number of cases, subtract the product of the number of groups in condition A and the number of groups in condition B. So here that would be, let's say if the sample size was 24, it would be 24 minus 6. Or another way you could do it is the number of cells, which is 3 times 2 is 6, multiplied by the sample size per cell minus 1, but that assumes equal sample size. So for the between degrees of freedom, we would take the number of groups in the effect subtracted by 1. So since there's 3 groups for therapy, it would be 3 minus 1. That would give us 2 levels of degrees of freedom for the therapy group. And then for gender, it would be 2 minus 1 because there's 2 levels of gender minus 1, and we would have 1 degree of freedom for the gender group. And then for the interaction, we would just take the 2 degrees of freedom and multiply them by each other. The degrees of freedom for therapy and the degrees of freedom for gender multiplied by each other would give you 2 times 1, which is 2. Alright, so finally we need to create what's called the mean squared from the sum of squares. So we have sum of squares between, and sum of squares within, and sum of squares for the interaction, and sum of squares between actually for the 2 main effects and the interaction. We need to create the mean squares within, and basically to compute that, you take the sum of squares between for each effect and divide it by the degrees of freedom for each effect. So that gives you the MS between, and we'll do the same thing for within. We'll take the sum of squares within and divide it by the degrees of freedom within. And then once we do that, we're able to compute the F ratios, which are basically the MS between for each effect divided by the MS within. So that will give us the F ratio for therapy, the F ratio for gender, and the F ratio for the interaction. And this is really what we're going to use to determine the p-value. So in the olden days, we'd look it up in a table like this and see, okay, with how many degrees of freedom for error and how many degrees of freedom for the effect or numerator, how do we have a significant F ratio? But if you're using SPSS, it will give you the p-value for each F ratio that's output, so you can compare, as we've been doing all along, your p-value to your alpha for the test. Alright, so now things, you can, assuming you have your results, your F ratio for the main effects, one for each main effect and one for the interaction. Let's say you have a significant interaction. Let's say, that you have a significant main effect. If there's only 2 levels, you don't have to do anything more because you'll know the nature of that difference, because there can only be a difference between those 2 groups. But if you have a main effect with more than 2 levels, then you'll just need to do post hoc tests, or if you have a specific pattern that you expect those means to differ by, you can do a planned contrast. So this is very similar to what we did with the one-way ANOVA. You can ask for Tukey tests or Bonferroni comparisons within the main effects, or if you want to, you can code certain planned contrasts. We would also want to compute effect sizes for our effects. SPSS by default will give something called partial eta squared. The formula we're looking at right now is eta squared. Eta squared will tell you the proportion of the total variance that is explained by a given effect, so a given main effect or a given interaction. So to calculate that, we just basically take the SS between for each effect and divide it by the SS total. But SPSS will give partial eta squared, which can be interpreted as the proportion of the remaining variance that a given effect explains. And by remaining variance, I mean we take out the other effects. So let's say for therapy group, the partial eta squared for therapy group would be the proportion of the variance explained by therapy disregarding the gender variance and the therapy by gender variance. So you can see the denominator in partial eta squared is not total, it's just that particular type of sum of squares and the sum of squares error, and it does not include the other main effects or interactions. So this is the one that is reported by SPSS. There are actually a somewhat large number of potential ways to report effect sizes from an ANOVA, but for now we'll stick to just a couple. Another one you might encounter is Cohen's F, which you can interpret as being a measure of the average standardized difference between three groups. It's kind of an extension of Cohen's D, but for ANOVA designs. So according to Cohen's conventions, a small Cohen's F value would be 0.10, a medium Cohen's F value would be about 0.25, and a large would be about 0.4. Alright, so to return to what do we do if we have an interaction? If we have an interaction, we have to do something called a simple effects analysis, which you can kind of think of as being like a follow-up analysis to probe the nature of the interaction. So as we've already noted several times, a simple effect expresses the differences among the means for one IV at a fixed level of another IV. So as we've seen before, let's say if we want to look at the simple effect of therapy group when gender is male, we will be looking at this comparison. When gender is female, we'd be looking at that comparison. We could also look at the simple effects of gender at each therapy group. That's probably a less interesting comparison, but it's something that we could do. So here we have simple effect of gender for the control group, simple effect of gender for art therapy, and simple effect of gender when it's the behavior modification condition. So you could analyze simple effects every which way, and if you're just practicing them, it might be good to analyze them analyze all the simple effects, but usually you have kind of predetermined ones that are of interest or ones that were hypothesized, and that's probably the way you would want to analyze it. So let's say you hypothesize that the genders would respond differently to the types of treatment, then you would likely look at the simple effect of gender and treatment type. Alright, so how to get these simple effects? So most everything in this lecture so far in SPSS you can get quite easily through the point and click menu, and it's demonstrated in a separate video how to conduct a factorial ANOVA. But for the simple effects, you actually have to add a bit of code. So you have to paste the syntax. So before you run the analysis, instead of clicking OK, you will paste the syntax and add the bit of code to tell SPSS in the estimated marginal means table for the interaction. So this is the table that's going to report the cell means. Add a bit of code that says to compare whatever it is you want to compare at fixed levels of the other IV. So this would compare gender at each level of treatment group. Right? Now, if you wanted to compare treatment group, you would instead put compare, since we've called treatment group in this code, compare group. And then this bit of code on the end here is just an adjustment for type 1 error, which is often not a bad idea, especially if you're doing a bunch of simple effect analyses. You might want to adjust for type 1 error, although this adjustment, the Bonferroni adjustment, is a fairly conservative one because it takes the alpha and divides it by the number of comparisons. So if there are a lot of comparisons, your alpha is going to get prohibitively low. Alright, so the output might seem a bit daunting at first, but if you look at the table at bottom, we see that it gives us basically the difference between males and females at each intervention group condition. So we see, okay, males and females control group, p-value is quite high, there's no difference. Males and females art therapy group, the p-value is fairly low, and especially since we've used the Bonferroni correction, it's low even despite that correction. So we see that males are significantly have significantly lower scores than females in the art therapy group, and then for the behavior modification group, we see that males have significantly higher scores than females, and that p-value is also quite low. So that's where the differences are, and that also kind of explains the nature of the difference between the simple effects, because this part of the table here gives you the simple effect of gender at control group. This gives you the simple effect of gender at art therapy group, and this gives you the simple effect of gender at behavior modification group. And this table will give you basically an interpretation of what a one-way ANOVA would look like at each group. So not the pairwise comparisons. Actually, the previous table with the pairwise comparisons, this is often called, instead of simple effects, this is often called simple comparisons, or I would call them simple pairwise comparisons, which are usually ultimately what you want to interpret. But we'll also get output looking at what is the effect of the IV taken together on the DV at various levels of the independent variable. Actually, these are identical to the previous ones because this IV that we were comparing only has 2 levels. But if it had more than 2 levels, we might see a difference because this would be the main effect, where this would actually be the pairwise comparisons within the levels of the other independent variable. If we wanted to look at it the other way, like I said, we can just add this bit of code that said compare and then put in parentheses group instead of gender, and we would get the output looking at it the other way. So here we're comparing the groups, the therapy groups at each level of gender. So control group versus art therapy, we see there's a difference. Control group versus behavior mod, we see there's a difference where the control group has higher scores than the art therapy and behavior mod. We see art therapy and behavior mod. For males, there really is no difference. For females, art therapy and behavior mod, there is a difference. So that's another thing that we would probably note if we were reporting this as a write-up of the results, a report of the results. Alright, so that wraps up the lecture for Factorial ANOVA. I know that's quite a lot to digest. You'll want to make sure that you read the associated chapter in the textbook and that you also review the tutorial for how to conduct a Factorial ANOVA in SPSS. I think that's probably more practical to digest at this point, and then to also complete the exercise on Factorial ANOVA, and be persistent, and I think some of this will start to make sense for you. Alright, thank you for listening. I hope you enjoyed that as much as I did.